to introduce you some the mechanism of MapReduce, how the MapReduce is designed and why it is designed like that. Okay. So the MapReduce, this is from the paper published by Google in OSDI in 2004. So if you know, you have some research experience or research background, you should know that OSDI is one of the best conference on operating systems and operating systems. So the paper is called MapReduce Simplified Data Processing on Large Clusters. So you could see that actually it's published almost 15 years ago. And if you are interested, you can go to this link to see the more details of the paper. And this project is mainly led by Jeffrey Dean, called Jeff Dean. So this is a programming model for parallel data processing. So in this paper, it mainly describes the MapReduce programming model and abstract operations by map function and reduce function. And then the paper tells you that how Google used this programming model for big data problems within Google. And because this is in Google, within Google, so it is not open to us. And then Hadoop, this project, began to adopt this programming model and design the Hadoop MapReduce. So this is open source software for us to use. And for you guys who have attended yesterday's lecture, so you have already installed Hadoop and configure it in the virtual machine image and also try to test the word count. So at least you can see roughly how it's like. And I support many languages such as Java, Ruby, Python, C++. So in this course, we will only use Java for programming and for the labs, for the projects. And so that's why Java is a prerequisite for this course. You must be able to produce Java code, Java project on your own. And MapReduce is mainly used for large-scale data processing in a distributed environment. It exploits large set of commodity computers. So compared to the traditional relational database, which use expensive hardwares, expensive servers, for MapReduce, it tries to explore large set of cheap computers to obtain very powerful computation. And it executes process in distributed manner. So within a cluster, there are many computers, and the map and reduce functions are executed in parallel. And it offers high availability. So it means at any time, this cluster is able to provide you the computation power for you to use to solve your big data problems. And so why Google designed this programming paradigm? So you can think about as Google, as such a big company, what this company need to do, and just think about the search engine. Okay, so all over the world, Google need to crawl the data from the websites to store in their servers in order to provide the search results for all the users. And so this is a video which shows the server room in Google. So you can see there are a lot of servers in the Google company. They are used to store the data crawled from the websites all over the world and to use for the processing the queries from the users. When users submit a query, some keywords to describe what he wants to search for, and the query will be processed in the big server, the server room. And so without MapReduce, there's a lot of problems need to be considered for the query processing. And so just using the Google search, web search as an example, assume that, okay, one user submits a query to the server, right? And you need to return the web pages relevant to this user's query and display the result to the user. And you also need to rank the document, the websites to the user, right? The most relevant should be ranked the highest, And as a result, the user could see the most relevant result in the first page. But the problem is that there are so many websites, so large data sets, how you can find the relevant web pages from such a huge data set. And it's not possible to store the huge data set, huge websites crawled from the other sources in a single machine, right? You must store this in a distributed environment to store this data set in a lot of disks, a lot of computer nodes. And for this query, then the problem comes, for example, okay, so how you can do this query processing in parallel? How you can search the data from different nodes simultaneously? You cannot just scan one by one, right? It is not possible for the user to wait for so long time to get the results. And how you can assign the tasks to workers distributed across potentially large number of machines. In this cluster, there are so many machines. And so given this query search problem, given this search engine problem, so although you can divide this into different small tasks, but the problem is that how you can assign these tasks to different workers and how you can guarantee that these workers can get the data they need. And also the synchronization problem and data sharing problem. And the last and also the most important problem is that how to deal with errors and faults. Because there's so many machines in the server room, so almost at any time, there may be some machine may have some problem, a disk failure or network failure, or even some other hardware problems. So it means that the data stored in that computer is lost during your tasks is being processed. How you can deal with such errors and faults? Well, without MapReduce such system, as the Google company, I need to think about all these details to process even a simple problem over a large data set, right? So that's why MapReduce is designed. I try to provide abstraction and that hides many system-level details from the programmer. Okay, I try to separate the what from how. So as a programmer, you only focus on the problem itself, focus on how to solve this problem. Well, you do not need to consider the low-level details, such as failures and how to assign tasks, how to do the data synchronization. These are low-level or system-level details. And these will be processed by MapReduce, by this framework. And it addresses this challenge by providing a simple abstraction for the developer. And so you already know mainly two main abstraction, map and reduce functions. And it handle most of the details behind the scenes in a scalable, robust, and efficient manner. So scalable means that you can easily scale the existing cluster by adding more cheaper machines. And robust, it is very reliable, and the availability of this cluster is very high. And efficient means very fast. It can provide a very fast problem-solving mechanism for your problem. So Jeff Dean lead this project, and I'm not sure if you know this guy before. And actually, this is a very famous scientist and also a programmer and engineer. And so if you are interested, you can try to search who is Jeff Dean. And you will see some jokes about Jeff Dean called Jeff Dean Defects. He's currently a Google Senior Fellow in the Systems and Infrastructure Group. He has already successfully finished many projects, including MapReduce, Bigtable. And last year, he also published a very important paper relevant to database. It's about trying to use machine learning techniques into indexing the big data. And so I just list some of them. I searched them from the website. And it's very, I think they are written by the colleagues of Jeff Dean from Google. So the speed of light in a vacuum used to be about 35 mph. And Jeff Dean spent a weekend to optimizing physics. And Jeff Dean once beat a spider. The spider got superpowers and sees readability. And Jeff Dean puts his pants on one leg at a time, but if he had more than 2 legs, you would see that actually his approach, the complexity is all log n, not all n. And compilers don't warn Jeff Dean warn compilers. And the rate at which Jeff Dean produced code jumped by a factor of 40 in late 2000 when he upgraded his keyboard to USB 2. Oh, this must be a very old joke. Okay, it's USB version 2. So there are many jokes about Jeff Dean. And this is a very famous guy. He's again still in Google, leading many interesting projects. And you have seen this before about typical big data problems. So the steps you need to follow to deal with the big data problems. So given you a large data set, what you need to do, you need to iterate over a large number of records, means scan the data set, and extract something of interest from each. So for your problem, this record may have many attributes, but your problem does not need to use all of them. So only some of the attributes are useful for your problem. So you need to extract these useful attributes from the record. And then you need to deal with this extracted information and generate some intermediate results for processing. After you process all these records, get all the intermediate results, you need to do some kind of operations like shuffle and sort and aggregate these intermediate results to generate the final output. So these 5 steps can be mapped to map and reduce function. So map will be, in MapReduce, map is used to read the data. So each time it deals with one record represented by a key value pair. And then within the map function, so for this given input, you need to define what you want to process this piece of record. So that's within the map function. And some intermediate results will be generated by your defined map function. And within the MapReduce system, okay, these results will be exchanged across different mappers, across different machines. And these intermediate results will be organized. And then for aggregation to generate the final results is in the reduce step. And the key idea is that, so this system, this programming model, provides you a functional abstraction for the 2 operations. So what you do is you use map and reduce these 2 abstraction functions, and you define within the map reduce function what you want to do to deal with, to process the data you read, and then to generate the final output. Okay. So let's review the word count example again. So last lecture, actually, I have already shown you the basic steps of word count in MapReduce. Now let's think about this process, whole process again. So given you a huge document and what you can do, and so without MapReduce, well, you can use you can split this huge document into different blocks, block 1, block 2, block 3, block 4, and for each block, for each piece of data, you send this block to a computer for processing, and in each computer, based on the data it receives, it can generate some partial results. So for this word count example, it can do some partial count to compute the term frequency within the data it received. And then finally, after all these partial counts are obtained from different computers, so you can merge them together to get the final results. And so actually, this the whole step enclosed by this red rectangle, kind of you can think of as a black box of MapReduce. So what you give MapReduce is you give the huge document to MapReduce, and within this part, MapReduce will process this huge document for and to generate the final result. So finally you get what you want. And The idea of MapReduce actually comes from functional programming. And I know that you have learned the object-oriented programming, such as using Python or C++ or Java. So someone may have some background knowledge about functional programming, but someone may not. So functional programming is different from object-oriented programming. So the idea is that in object-oriented programming, you view everything as object. Okay. So in functional programming, you can think about that. You view everything as a function, and the functions can be used as just like used as an object in the object-oriented programming. For example, in a function, you can pass this function as a parameter to another function, and you can also return a function as a return value for a function. And so in MapReduce, you can view map as a transformation over a data set. So this transformation is specified by function f, and each function functional application happens in isolation. So on different machines, and these function f are used to deal with different sets of data sets. So they happen in isolation, so they do not depend on each other. And application of f to each element of data set can be parallelized in a straightforward manner. So it just need to deal with data it receives. And f is defined by us. And we can view reduce as an aggregation operation. So the transformation means that, so given you a piece of record, then you transform this record to another format. So if you remember for the map function, it receives a key value pair, right? And it generates a list of key value pairs. So this is a kind of a transformation. Transform the given key and value pair and generate a list of key value pairs. In the word count example, it receives a document as a value and document ID as a key. And so it just counts the number of terms within this document. And the result is a list of terms and the local term frequency, or the local count for this term within this document. So this transformation. And for different problems, you define the different transformation method. So in word count, the transformation is to transform the documents to the list of terms and their local count. But for other problems, you need to define your own function to do the data processing. For the reduce step, you can view this reduce step as an aggregation operation. So after you get some partial results by using the map step, the transformation, transform your original data to some intermediate results. And aggregation happens in the reduce step. It aggregates the intermediate results, the partial results, to generate the final output. So we can think about aggregation is defined by the function g. And elements in the list must be brought together. So from different mapper output, all the values relevant to the same key will be grouped together and attached to this key. And as a result, what the reducer receives is a key and a list of values. And these values are collected from all the output of all the mappers. And next, within the reduce function, and you define how to do the aggregation. So for what counts for this example, G is just a sum. It sums all the local count from all the mapper output, and then add them together. So actually, you get a global count from all the local counts. So if you can group the elements of the list, then the reduce phase can also proceed in parallel. In the word count example, it means that for the different terms, you can set them to different reducers. And the aggregation for different terms, actually, they are also independent to each other, right? So you compute the count for this term. It does not matter how you compute the term or the count for another term. So the word count computation for different terms can also happen in parallel. So you can also do this step in a distributed manner. So the framework will be in charge of, will take charge of the coordinating the map and reduce phases. It means that all the other details are hidden by the framework. And what you do is kind of to define the function f, how to do the transformation, and how you define the function g, how you do the aggregation. So that's the two things you need to focus on. But for the other things, so if you remember about the challenges for big data problem, such as data synchronization and data sharing, and dealing with false errors, these things are not a problem for us now because MapReduce will handle all these low-level details. So that's a basic idea for MapReduce. And so next, I'll introduce the structures used in MapReduce. Key value pairs is a data type, the basic data structure in MapReduce. And key and values can be integers, float, strings, and raw bytes. And they can also be arbitrary data structures defined by yourself. But you need to follow some steps to define your own data type as keys and as values. So this will be introduced in later slides. And the design of MapReduce algorithms involves, so first you need to impose a key value structure on arbitrary data sets. And you need to think about what can be the key and what can be the value. What is the data type for the keys and what is the data type for values? So for example, for a collection of web pages, for example, in Google, and the input keys could be URLs, right? So one URL can identify a web page uniquely. So it can be used as a key. And values is just the HTML content of this web page. So here you need to guarantee that the key must be able to identify this record or this piece of data uniquely. So that's very important. And then in some algorithms, the input keys are not used. In word count, actually, you can see that document ID is not useful. We only care about the document contents, and we don't use document ID. But in some other problems, the keys are also very useful. And the keys can be combined in complex ways to design various algorithms. So it means that the keys could be a pair of objects or some other kind of complex objects, not just a single value, integer or string. And for different problems, you need to think about how you can define your own keys to deal with a problem efficiently. So we have seen this before, and I just try to emphasize the whole data types used in MapReduce again. So as a programmer, we only need to specify two functions, the map function and the reduce function. For map function, it transforms a key value pair to a list of key value pairs. In word count, so this is a document ID and document contents and a list of terms, and the local count of this term in this document represented by V1. And so in this map function, it transforms the input into key value pairs for later processing. And in the reduce function, what it receives is a key and a list of values for this key. So this list of values are obtained from all the map output. So for one map output, you get some values for this key. And for another map output, you also get some values for that key. So in MapReduce, it will group these values for the same key. And then this key and a list of values will be sent to a reduce function for processing. And within this, you can generate also a list of key value pairs as a final output. So in word count, this is very easy. For a key, a term, a list of values, a list of local count, you just do a sum. And the output is a key, the term, and the final global count for this term is a value. And so in the reduce function, it aggregates a list of values for each key. And all the values with the same key will be sent to the same reducer for processing. And so the MapReduce environment will take in charge of everything else. Now you only need to focus on map and reduce. The first thing is to think about what should be the key and value for input and for the output. So for the word count problem, okay, so it's easy to identify that the key as input key value pair is document and document ID, and output is term and term value, term count. But for some complicated problems, it's not that easy to identify what should be the data types for your input and output. So this is a very simple structure of MapReduce. So one round MapReduce for most problems may be already enough. But for some other complex problems, so just one round map and reduce may not be enough. So which means that you need to chain these map reduce jobs. So map, reduce, and from the reduce, you get some output, and these results are stored in HDFS. And next, you need to chain another map after this reduce step. So the next map function will read the output of the previous reduce as an input, and then reduce the next round reduce to generate the step in the next step. We will see these chained MapReduce jobs when we learn the graph data processing. Okay, so what means everything? Oh, thanks.
The output is always key value, or can I, for example, nest key value, but this value is other key value and so on? Or the output is always default key value, that's it?
The output is always key and value pairs in MapReduce.
And this value I cannot substitute with an object, something like that, for example?
You can define your own data types for these values or keys. That's okay. But I mean, the format must be key and value pairs. Yeah. Okay. And for everything else, so if you remember, and previously when we talked about the challenges for big data processing in both last week and this week, previously, you can see that there's a lot of system level details, such as how to handle the scheduling, how you can assign workers to map and reduce tasks. Because for a large data set, so if you, so the number of map functions is exactly the same as the number of records in a data set, right? So you have a lot of map functions. And for reduced tasks, there may also be may have a lot of reduced tasks. This is specified by you. But for huge amounts of tasks, how you can assign them to your cluster nodes. So say in your cluster you have only 100 nodes, but for these map reduced tasks, maybe you have tens of thousands. How do you can assign a huge amount of map reduced tasks to just 100 nodes? MapReduce will do this for us, and also handle the data distribution, how to handle the partition of the data. What you are given is a huge data set, but the data is how the data is split into small chunks, right? So this is actually what HDFS does. So we will learn HDFS later. So in HDFS, one chunk will be used to store some piece of data, and we will not move the data to the computation node. You see the difference. So assume that you have a computer, and assume that your map task will be run on this computer, and your data is in another at another place, for example, on a disk of another computer. So traditional ways is that you need to fetch the data from another computer to this computer for processing, because I assume that the worker will be run on this computer, right? So that's traditionally how the distributed computation is computation works. But in MapReduce, that is because this way is not efficient. Moving the data has very high cost, the network cost and also I/O cost. So as a result, in MapReduce, it moves process to data. So where the data is and where the data processing happens. So as a result, you get rid of the data moving cost. And also about handle synchronization and how to deal with the intermediate data is also handled by MapReduce, and also errors and faults. So anyway, so everything happens on top of distributed file system, and is also dealt with by MapReduce. So as a result, besides map and reduce, the two functions, so you never know that where the mappers and reduce run. So given your cluster, you do not know on this node how many mappers assigned to this computer and which mappers are assigned to this computer. And when a mapper or reducer begins or finishes, so the scheduling is performed by MapReduce. And which input a particular mapper is processing, you also know. And you just know that some map function is invoked for a given piece of record. And which intermediate key a particular reducer is processing, you also know. You just know that, okay, this key will be sent to some reducer, but which one, you don't need to care about. You don't need to care all the system level details. So what you need to focus on is just map and reduce what map function should do and what reduce function should do. So you can see that now a big data problem is much, much easier.
Who's in charge for launching all these workers? Is the user? The user can limit the number of workers, or Hadoop stays in charge of all these?
It depends on if it's a mapper or reducer. So for mapper, it depends on the data. So if you see the structure, you can see for one record, there will be one map function, right? For reducer, well, this depends on you. So you can specify how many reducers you want to use in your cluster, okay? So how many reducers do we want to use? Actually, it's kind of the only things that we can control in MapReduce. Yeah. So a brief view of MapReduce is like this. So you have a data set, key value pairs. And for the key value pairs, each key value pair will be processed by one map function in mapper. And the map function will transform a key value pair to a list of key value pairs. So in this example, you can see each map function generates some intermediate output. And next, there's a step called shuffle and sort. They will aggregate these values by keys. So shuffle and sort means that the data will be shuffled first and then aggregated together. So the values for the same key will be grouped together. So for example, A1 and A5, they will be grouped together. They are from different mappers. And sort means that the keys will be sorted and based on the values of these keys. And then the intermediate results will be sent to different reducers for processing. For this step, we will see more details in later slides, but here you just need to know that for the intermediate result generated from different mappers, well, here MapReduce will group the values for the same key and sort the keys and then send the key value pairs and group the key and the grouped values to the reducers for processing. So here in this example, so A I sent to this reducer, B sent to this reducer, and C sent to this reducer. And to generate the final output. So this is a brief view of MapReduce. So later we will learn more details so we can see a more complicated view of MapReduce, the structure. Okay.
Yeah, previously you said map and reducer is kind of like function programming, and the number of map and reducer, number of map is determined by the original raw data.
Yeah.
So what if all the maps have the same function like the word count? We still, like in this case, we always need 4 maps. Even every map, they have the same function.
You have only one map function, right?
So map and map function is different.
No, I mean, so you only have one function to describe what the map can do. So such as in word count, you can only tell MapReduce, okay, you just need to do a local count for a given document, right? So that's what a map function can do. And number of mappers means that in the system, how many times a map function need to be invoked for a data, for a record. Okay, and
Same with reducer.
you mean the name for them?
No. So what is the number of reducers?
The number of reducers, as a site, you need to tell MapReduce how many reducers you want to use. So by default, it's only one reducer. But if you want to use more reducers, you need to, within your program, you need to use a function set number of reducers, 2, 3, 4, to tell MapReduce how many reducers will be used.
So if in map you said map and map function is different, so if I just have one reducer or reduce function and I run it like 7 times, so I have 7 reducers.
What do you mean by run 7 times?
Because you said if I just have one map function and I run it like 4 times, 7 times, which means I will have 4 mapper. And what is this process in the reduce? So
So you still get confused about the whole process, right? Okay, I'll try to explain again. Maybe some concepts I didn't describe clearly, I guess. So for map and reduce, the map function and reduce function is the function you define. Okay, you tell MapReduce what you need to do in the mapper and what you need to do in the reducer. So for the word count example, okay, in this example, you have only one map function, one reduce function. So map function just read the input document and do a local count and generate some intermediate results. And for the reduce function, it gets key and the list of values. And these values are get from all the map output. And the reduce function will do the aggregation to generate the final global count for this term. So that's a map function, reduce function. And for mappers and reducers, so because one piece of record, one record need to be processed, you need to invoke one map function for this record, right? So I call this a mapper. Still not very accurate, but actually you can think like that this on different, in your cluster you have like many computers. On each computer you have some data, right? And this data must be processed by a map function. And so I call this the mapper dealing with some data. Okay. And for the reducer, it's the same. If assume that you have only one reduce function, one reducer, and it means that only one computer node will be used to run the reduce function. And all the key value pairs, the key value pairs, will be sent to this computer for processing. And so that's only one reduce function. But if you have, in this example, you use 3 reducers. So it means that you need to use 3 computers. Not very accurate. Actually, it depends on, 3 nodes, kind of, not computers. So you have 3 reducer to deal with the grouped key value pairs. But which key is processed by which reducer? You also need to use something to do a computation. So we will learn later about this called a partitioner. So when there's more reducers, this key, for example, this key A is sent to this one, this one, or this one. You need to specify. You need to define some function to tell MapReduce how to send this key and the list values to a reducer. But anyway, if you are more than one reducer, then the key and group values will be sent to different nodes for parallel processing. And as a result, you have 3 outputs. So reduce function is as an abstraction. And it tells MapReduce what it needs to do. And reducer is, you can think a node that runs the reduce function for some data. Okay.
Professor, I know that we can decide the number of reducers, but what decides the number of maps?
So as I said, it depends on the data.
Yeah, but for here, we have 6 value pairs.
Oh, just a very simple example. Here, you have 6 key value pairs. You need to invoke 6 times map function to deal with the 6 key value pairs. Yeah.
So how many different words we have?
Not words, documents. So remember the word count. Here, the input is the number of documents. Yeah, the data source.
I got it. Thank you.
Yeah. For shuffle and sort, it's in between the map reduce step. And on a mapper, so it generates some output. On each mapper, there's some output. But the problem is that how to group these data for the same key and send to the reducer. So that's what shuffle and sort do. So shuffle will input to the reducer. Shuffle will do a kind of group step for all the key value pairs. So group the values for the same key. And the framework will fetch the relevant partition of the output of all the mappers using HTTP protocol. And sort is to do a sort for the keys according to their values. The group the reducer inputs by keys in this stage. And this happens when there are more than one reducer. So in previous example, if you use 3 reducers, so sort step will first sort the keys according to their values, and then partition the key space into 3 parts. And the first part will be sent to the first reducer for processing, and the second part will be sent to the second reducer for processing. So it means that the key value pairs, the reducer will be sent to which reducer. It depends on this sort phase. Sort do the sorting for the key values, and then this decides a key value pair is sent to which reducer for later processing. So a figure can be shown like this, not very complicated figure. Just show the basic steps. So this is input, and the data is obtained from HDFS. So split 0, split 1, split 2. We have 3 chunks of data for different mappers to process. And within the mapper, it will generate some output. So here, they will first do a local sort for all the keys. So you can think about this as a local sort for the terms by alphabetical order. And then in the reducer, they will fetch the data from the different mappers and then merge them together for the reduce function to process. So in between, it's called the shuffle and sort step. We can ignore the shuffle and sort steps right now, so we just focus on map and reduce. So you can just assume that we have a map function, and the map function is kind of a transformation. It transforms the given input to some intermediate result. And the reduce function is to get the input of a key and a list of values. These values are collected from the output of all mappers. And then in the reduce function, I do aggregation for these values of the key to generate the final output. So that's what we need to focus right now. And for simplicity, we can only just assume one reducer, just one reducer, not too many reducers. And later, we will go to more details about the shuffle and sort, about the number of reducers, using more examples. So a brief data flow is like this. All the data, as a given data, is stored in HDFS. And HDFS, on HDFS, there's the data chunks. So each chunk is used to store some data. For example, 64 megabytes or 108 megabytes per chunk. And your given data set is split according to the size of the chunk. And the input will be sent to the mapper for processing. And the mapper will invoke the map function to deal with each piece of record received by it. And the generated intermediate results will be shuffled and sorted, and then so it means that the values are grouped together for the same key, and then for a reduce function to process to generate the final output. Okay, just a brief data flow. So like as a site, now we just get rid of the details. We just focus on map and reduce, and think about only one reducer, and we try to solve some problems. So this is a hello world program in MapReduce. It's a word count. So this is the example we have already seen in the last lecture, right? We have 3 documents. assume that the 3 documents are split into 3 different chunks, data chunks, and each is processed by one mapper. And in this mapper, it generates some intermediate results here, also some intermediate results here, and then shuffled and sorted. So the terms, the key value pairs are sorted according to the keys by alphabetical order, and the values for the same key are grouped together. So you can see for bear, all the ones for this bear term are grouped together, similarly for car, deer, and river. And then reduce function do an aggregation for each key and a list of values. So we assume there are only one reducer. So all the grouped key and values are sent to a reducer for processing, and we generate the final word count result. Using pseudocode to represent, so you can see what does the mapper do. Mapper takes document ID and document key value pairs as input. And in this map function, it's very simple. So for each term within the document, you just emit a key value pair with this term and count 1. So term and 1 will be sent out from this mapper. So this is an intermediate result obtained from this map function. And for reducer, now the reduce function receives a key and a list of counts collected from different mappers. So in this example, for example, for a car, so we have car as a term T as key, and counts, there are 3 ones in this list. And the reduce function is just do aggregation, do a sum for all the values received for this key, and then emit the term and final count as output. So this is the global count, because you have already added out local count to generate the global count. Okay, so that's hello world in MapReduce. I guess algorithm should be very easy to understand, right? So I don't want to explain further. So now, just want to try to explain how to implement such a pseudocode, such a hello world program in MapReduce. So given your problem, so what you need to do first is always to think about the data types, about input key value pairs. So in this problem, okay, the document ID and document is the record you want to use for map function. So this is a unique identifier for this document, and it is the document, the content of this document. And the mapper will do first it will tokenize the string to separate the string into words according to tokenizers such as space, a comma, or some other characters. And then for each tokenized term, it emits the key, the term, and the value 1. And the framework will guarantee that all values associated with the same key, the term, grouped together, are brought to the same reducer. And in the reducer, we receive all values for the same key, and then do aggregation, do a sum to compute the global count. So this is the structure of the Hello World program in MapReduce. And this is some other low-level details within MapReduce, such as how to do coordination. There is a master node in MapReduce. So the master node will take care of the coordination, including the task status, and which task is idle, in progress, or already completed, and other tasks get scheduled as workers become available. So, so in your cluster, if there are some workers available, then a task will be sent to that worker for processing. And if a map task completes, then it will send the master that my location, where is my location, and the size of my intermediate results. Because later, the reducer need to fetch the data generated from this mapper for later processing. And in order to detect failures, so the master need to ping the workers periodically in order to check if there are some problems. And here is some ways how MapReduce deals with failures. And there are different types of failures, including map worker failure, reduce worker failure, and even the master may fail as well. So for different type of failures, MapReduce has different mechanisms to deal with them. And So for map work failure, so a task will be reassigned to another map worker. And for reduced work failure, well, its task will be reassigned to another reduced worker, and the reduced task will be restarted. And if you already have all the mapper finished, then you don't need to invoke all the mapper tasks because the intermediate data is already there. You just need to fetch them from the mapper and then rerun the reduced tasks. That's already enough. So this, according to the Google's experience, once they lost 1,600 computers out of 1,800 machines, but they still finished their task. So you can see that MapReduce is very robust to failures. And about why MapReduce is so efficient and effective for big data problems, or we call where the magic happens within MapReduce. Basically, it's because of this parallel group by operation on the intermediate keys. So the intermediate data arrive at each reducer in order and sorted by the key. And so that's one feature in MapReduce. So still use word count as an example. You have, for each mapper, you have a list of terms and the local counts. And then in the shuffle and sort step, and the parallel group by will be applied to these key and values. And the values associated to the same key will be grouped together. And then this key and the list of values will be sent to the reducer in order, according to some order specified by you. And within one reducer, the order is guaranteed. And the output keys from the reducers are written back to HDFS as well. So your data is in HDFS, and then the output from reducers are also stored in HDFS. So the output may consist of R distinct files, and how many reducers you have, and how many distinct files you will generate on HDFS. Such output may be input to a subsequent MapReduce phase. So at the site, there may be chain tasks. So the output of this reduce step in the current round may be the input of the map in the next round. And the intermediate keys used in the shuffle and sort phase are transient. So they are not stored on the distributed file system. They're stored locally, and that's built to the local disk of each machine in the cluster. Well, these are actually the low-level details. I guess it's not very easy to understand why they are helpful for the efficient big data processing in big data. So I try to skip these steps and go to the next step about how to write the word count in Java. I think that's more practical for us to learn MapReduce. And you will also practice this in the first lab and also in the lab in the next week. Okay, so we first have a short break, and then we next begin to learn how to write the practical word count program in MapReduce. Okay.
What happens, for example, if I pass, I'm going to map many files, alright? But one of these files is bigger than a chunk. Does MapReduce like divide this file or not?
So you mean one file is bigger than the data chunk?
Yeah.
I think normally this will not happen. You think about normally one chunk is more than one megabytes. So one file is larger than this. It's very rare. But okay, so assume that there's some case like this. So how much will deal with that? And it means that it will read not one chunk, it will all the chunks relevant to this record, okay, we call this record, and read them to, we will process them as one record. So that's how it will MapReduce will deal with it.
So they are not limited by the size of the chunk, which is 108 megabytes, right?
Because at your side, your file is so large and it cannot be stored in one chunk, it is stored in several chunks. But one map function is to deal with one such iteration.
So my map function should be able to divide this file. Or not?
Not one file. I need to scan all the chunks relevant to this file to get the intermediate results. So I'll still use this work on as an example. So assume that you have several documents to do work on. One document is so large, 200 megabytes, right? But it is stored in two chunks. Okay, so what does map function do? Map function will read the two blocks in memory and then for local count for processing and then generate output. So that's it.
Okay. Alright. Okay. And does the guy uses Hadoop to read big database, relational database, for example?
You read data directly from the relational database?
Yeah, for example, imagine that I have a huge database that someone is using only to store some data, only certain, but now I wanted to read this data.
No, in MapReduce, all the data are stored in HDFS. A MapReduce tab can read data from maybe from HBase, but HBase, the data in HBase is also based on HDFS, based on Hadoop distributed file system, not based on the other kind of file structures.
So I should convert this data from database
So you mean
to
you
CSV, for example.
already a big data in some relational database, and how you can use MapReduce to deal
Yeah, for
with that
example,
data.
Amazon Redshift. I have Amazon Redshift there, which is possible, alright? But it's too big, that stuff. I don't want to put more stuff. So I wanted to read some stuff with Hadoop, create some formulas, because Amazon Redshift is based with queries, alright? But sometimes I have such a complex function that Hadoop might help me. So how do I do this? This problem.
I'm not sure if the relational database can provide APIs for MapReduce.
I think Hadoop has API to connect with database.
I'm not sure if all the databases have such support to MapReduce. I can't be sure for now and to check. So
Java has like DB connections to connect all the things. So maybe you develop some program.
but that's Java, not the MapReduce. You have JDBC to connect to relational database.
Yeah.
The JDBC, but that's not part of Hadoop MapReduce. So you need to follow the MapReduce structure. So the MapReduce structure means that your map function will read some data from HDFS.
Okay.
Yeah, the data sources could be text file or binary files, but they must be stored in HDFS first. And our local file system is also okay. But,
So there's no advantage of using Amazon Redshift if you have complex queries to do, like complex logic behind it. It's better to save everything in CSV and put to Hadoop so you can calculate better. Got what I'm saying?
I understand what you mean. You mean your data is already there, and how you can utilize MapReduce to do some task, right?
Yeah, more complex task, you know? Because if you use queries, then you start with subqueries, then you start more nodes in Amazon Redshift. It doesn't solve, you know? You start creating views and all this stuff becomes a mess. You
Yeah.
change Java, you can fix it much easier, you know?
Yeah. I see. So I'm still not for sure if MapReduce can directly read the data from our existing relational database. I think normally you'll need to store the data in HDFS, and then MapReduce can read the data from HDFS. Or store in HBase. HBase is also can be an input source for MapReduce program. It's also okay. Yeah. That's
HBase is the same key value. Or
HBase is kind of a NoSQL system.
okay.
Yeah, NoSQL database. Kind of. It's a column-oriented database. Yeah.
All right.
But you can send more details of the question and can help to check if because MapReduce keeps evolving. I'm not sure if MapReduce can have more features to support different applications.
Okay. I will post on forum.
Okay, yeah.
The forum.
Yeah.
So I will draw WhatsApp.
Yeah.
Okay. Thank you.
我想问你一下，就是您上节课提到说我们那个 project 最好用 Java 写，就但是您也当时讲说就是可以用 Python 写， 说？
建议是不要用 Python 的话，这边做 evaluation 也比较麻烦。evaluation 的话，就是我们要写新的脚本，我们暂时没有 Python evaluation 的脚本，因为之前那个还要上。
哦，那行，那明白。
你是比较喜欢用 Python，不喜欢用 Java 是吧？
对，因为觉得比较用的比较熟了，而且因为之前做了一个就是 Spark 的项目在国内，然后也是用的，它整个项目全都用
Spark 那个用 Python 还比较容易，但是 MapReduce 这边用 Python 用非常比较难做。或者你考虑用 Spark 的时候，可能用 Python 做，因为那边是用 Scala 来做 program 的，那个用 Scala 还是用 Python 都差太多。但这边 MapReduce 的话，我对 Python 不是那么的熟，所以我不确定说如果再重新做一个 marketing 脚本的话，会多么困难。
咱们是那到时候再看吧，因为我不知道咱们是最后拿什么样去判断。如果只是拿 output 去比对的话，
其实就是拿出来，当然也会看你的 code structure，我会去看一下你的 source code。不过 Python code 也比较好懂，知道不？
就是因为它可能前面只是说 Java 后面加一个，然后你改成 Python 在里面。
也有，我也得需要跟 tutor check 一下，因为这个不是我来做的，那个 marketing script
行，那我们在等您消息的时候怎么样？
你还是说希望能用 Python 来做 program 是吧？
就如果可以的话，如果要是难度很大就算了，就尽量改成 Java。
如果说 Java 对你难度不是很大的话，赶紧接受 Java 来做，因为是这样，因为那个今年的学生比较多，所以说如果那个再弄的话 ，tutor 工作量会比较大，很多对，所以说比如说去年可能就几十个、10个、20个，我觉得更 flexible 没问题。那今年一下就是一些3倍的量，
行，那就还是找完了，谢谢。
你之前在国内做过有 Spark program
就银行现在也在做那种分布式系统嘛，
他们做自己的分布式系统，
也商用的买过来，然后买来改下来，
商用的自己改的。
然后现在核心也在做分布式核心系统，就银行核心系统在做核心系统。
那你实习的时候，
我在国内上
5班，那应该蛮有经验的。
谢谢。换时尚是还是一定要固定的？
一般来说，你要换的话，你是说你们互相换，还是说你们自己互相换？
就像这样，就因为我们就是一起而已。
这样子是吧？可能前几周我不确定，因为是前面都满了嘛。因为前几周大家都比较急性，后面来，后面的话就后面很多人都不来了，估计就懂了。
星期一来了，星期一。
我去查一下，有星期有2个来，现在有2个来。
上午。
下午。Okay, so let's continue the topic on writing Java code in MapReduce. So we still use word count as an example as a Hello World project for MapReduce. So okay, I assume that you already know Java programming, okay? And so in MapReduce programming, a MapReduce program consists of the following 3 parts. So first is a main function, or the driver, called the driver. This will use to configure your MapReduce job and also trigger the MapReduce methods. And the mapper class is used to define the map function. And reducer class is used to define the reduce function. And normally, it's better to include the MapReduce and the main method in 3 different classes. But if this is not a very complex problem, okay, you can also put all of them into one single Java file. It's also okay. And there's some, this is a reference for all the classes in MapReduce version 2.7.2. And if you get some problems, you can go to this website to check the details of the class you want to use. Okay, so now let's go to the source code, which is a little bit complicated and not very straightforward to understand and to view. Okay, this is just the code. Okay, and I'll try to explain the mapper and reducer code line by line. So for the mapper class, so this is a map class for word count. You need to extend the mapper provided by MapReduce and define your own class. So we call this a tokenizer mapper. So because in this mapper, we tokenize the given document to terms and then emit the key value pairs term and one. And you also need to specify the data types for the input key and the output key of the mapper. So the input is object because we do not use a document ID, so it doesn't matter which data type you use. So we just use object. And the document is a string, so we use text. So why we use text, not string in MapReduce? And so I will introduce this later. Text is kind of a wrapper of the string data type in MapReduce. And text is for the output of the mapper. So this represents the document, and this is the type of the term, the output key. Iterable, so it's a new class. Okay, so we do not use integer to represent the count. We use iterable, which is also a class provided by MapReduce. So this is used to wrap the integer in Java. And okay, so we have final static iterable value 1. So just used to wrap integer 1. And then we also have a text object word, new text. So this is a map function. Within the map function, you see we need to specify the input for this map function, the document ID, document content. And this context, this is object to store the context of the MapReduce jobs. And your output key value pairs are also stored in this context object. And you need to deal with some exceptions. Okay. So within the function, is the function body. Well, actually, it is very easy. So the tokenizer, you just invoke a tokenizer to split the documents into terms, and then you iterate over all the terms. And for each term, you get a key value pair, the term itself and one, and use the context objects to send the key value pair out. So that's it. The logic actually is very simple, but the problem is that we meet many new concepts, new classes, and new code structures. So that's where the difficult is. So for the details, I'll try to explain line by line. So for the mapper class, we need to we always need, so given the problem, you need to think about the data type for the input output. And when defining the map class, you also need to specify the data type for the input key values and output key values. Okay. And the class mapper is provided by MapReduce. So your mapper always need to extend from this class. So in order to make your map function can be invoked by the MapReduce framework. And this class has specified the input key and value and output key and value types. So you need to specify the data types when you extend from the mapper class. And in the word count example, okay, so key in and value in is just document ID document, and key out, value out, just word and value 1. Okay. For text and iterable, there are the serializable and comparable classes provided by MapReduce for us to wrap the primitives in Java, such as string and integer. And we need to use these classes because now we are not doing the serialization in our local file systems. Remember, all the I/O access is based on HDFS. So you read the data from HDFS and you write the data to HDFS. So these are different from what we do in a normal Java program. So that's why you are not able to use integer or string for serialization. That cannot be used in MapReduce. So you can try to see if what it will happen if you use string integer when you define a mapper. You will get some exceptions, and you can try this during the lab. So at this stage, you just need to know that because the serialization is different from the normal Java program because it is based on HDFS, not based on local file systems. So as a result, you need to use the serializable and comparable classes provided by MapReduce for the serialization, for the I/O access, for reading, for read and for write from disk. And here, this we just define interactable static interactable value 1 because for each term we will emit a term and 1. So we just define a variable here. So next, this a text object. So the key of the output key is a term, and because we want to we are doing this within MapReduce, right? So that's why we can't use string to describe this term. Instead, we need to use text, which is a wrapper class in MapReduce for string, to define the data type for the output key. Okay. So we will explain more details about these interactable or text, these classes later. So these classes are extended from a writable class in MapReduce. So writable class is kind of interface in MapReduce. So these classes implements writable, and so then they can be used for synchronization on HDFS. So Hadoop defines its own box classes for these primitives in Java, including strings, float, integers, and characters, and all these primitive data types. And for within the MapReduce program, all values must implement interface writable, and all keys must implement interface writable comparable. So it means that when you want to define your own data type, you must implement the interface corresponding interfaces. But right now, we just use the built-in data types provided by MapReduce. And this writable interface is a serializable object which implements a simple, efficient, and serialization protocol. So we do not need to know the details. We just need to know that, okay, so this helps us to serialize our data to HDFS and deserialize the data from HDFS. That's why we need to use the writable for writing and reading data in MapReduce. So in your program, when you write your own program, remember that you cannot use the Java primitive data types for describing the data type of key value pairs in MapReduce. Okay, you must use the writable or writable comparable data types provided by MapReduce to define the key and value data types. If the key is a string, you must use text. If the value is an integer, you must use interactable. Or if it's a double or float, you can use float writable, double writable to wrap your data, because this can help you to serialize and deserialize your data to HDFS and from HDFS. Okay, and so that's about the data types and some new classes. And for the mapper class, the main body is a map function. So the map function is defined by us. Okay, so in the map function, first you also need to tell what is the input data type, input key and input value. This must be consistent with previously when you define the mapper class. So this object text, if there's some inconsistency, you will get some exceptions or some errors. And so the context, this class is an inner class of mapper. So it is used to store the context of a running task. And in the mapper class, it is used to collect the data output by the mapper. In reducer, we also use this class, context object to collect data output for the reducer. Okay. And the exceptions need to be dealt with. So you do not throw these exceptions. Your program cannot be run by MapReduce. So this function is called once for each key value pairs in the input split. So your application must override this to do your own job. You must define the map function, and within the map function, you must tell MapReduce what you want to do, how you want to process the data received by this key and value for process your problem, for solving your problem. Okay. Okay, now let's go into the map function. So this is a Java class. Okay, so the string tokenizer. It will tokenize a document to terms. And by default, without specifying the tokenizer characters, it's just space. And the documents will be split to terms according to the space character. But you can also specify more tokenizers, more characters. And then next, you get a list of terms. You just iterate over these terms for each term. And now the term is of type string. So you need to convert the string type to the text type. You must wrap your string, your term, and as a text object, which is word, and then use the context object to write the intermediate result, word, the one, which is text and which is interpretable. So as a result, the term can be written to HDFS. So otherwise, you will get some IO exceptions without using text or interpretable. And map function produces a map context object and takes key value elements as input. And remember that any key must be readable comparable, and any value must be readable data type. So this is very important. And so that's a mapper. Okay, so let's go back to the whole program again. At the side, the logic is very, very easy. So you just need to tokenize the document you received in the mapper. And then for each term obtained by this tokenizer, you just emit the term itself and the value 1. But the concepts include how to define the mapper, how to specify data types, and what are the classes we can use to define data types, and how we can emit the key value pairs. So at the beginning, given you a new problem, I know that it's very difficult to write MapReduce program for this problem. So gradually, we will give you some problems similar to word count. So you will learn from learn the programming for some problems similar to word count, and to get more knowledge about MapReduce programming. And then later, you can do more complicated jobs. Okay. So about the mapper class, so if you have any questions. So if no, I will go to the reducer class. Well, after explaining the mapper class, well, the reducer class is a little bit more easy to understand because it's very similar, right? So this is a reducer, your own reducer. So you give a name for this reducer, we call int sum, because in this reducer we do aggregation. We sum all the integers for a key. And must extends from the reducer class provided by MapReduce. And also need to specify the input key value pairs and output key value pairs, the data types. And in the reducer, in this word count example, so what you receive is a term, text as a key, and a list of values and iterable. And what you generate is a term and a global count. So the output is also text and interactable. Within the reducer class, so we need to define a reduce function which tells MapReduce how you will do the aggregation, right? So remember what you receive is a key and a list of values. So here we use iterable, interactable. And this and this, the data type, two data types must be consistent with where you define here, okay? And again, we use the context to collect the output of the reducer. Within the reduce function, so the logic is also very easy. So you get all the values and just do a sum and compute the final count. And remember that now we are doing the serialization in HDFS. So the key must be of type text, and the integer must be wrapped by an interactable class. So the key, you see, key is just the term itself, text. But the result, so after we compute integer, we need to use interactable to wrap this value, and then use context write to emit these key value pairs to HDFS. So they will be sent to HDFS. Okay, so that's a reducer class. Some more detailed explanations. I'll try to give some of them because most of them have already explained to you. So here is about definition. You extend the reducer, specify the data types, and remember that what you receive in the text reduce function is a term and a list of values. So in this example, it's word and list of ones, right? And within the function, it's very easy, do a sum. But remember to wrap the strings and to wrap the integers as text and as interactables, and finally to write out. So that's the reducer. And here we finish the major tasks in MapReduce programming because we already tell MapReduce how a map function is like. So we tell MapReduce, okay, how you need to transform my input data to the intermediate results. And in the reduce function, we tell MapReduce how you need to aggregate my intermediate results to the final output. Okay, so that's finished. And the next step is just for the configuration and for starting up the tasks. So this is basic functions you need to use. And configuration object, this is used to configure your MapReduce task. And you also need to get a job object to get your job instance. And then using this job object, you set the your task class, it is work count class, and set map class, which is tokenizer mapper, and reduce class, and sum reducer, and also set the output key and set output value. So you may observe that we do not set the input key and input value, right? So actually, MapReduce has some default data types for input key value pairs and also for output key value pairs. And so in this example, we can just use the default data types. So we meet the input key class, input value class. But if you use some complicated keys or values in your own program, you must set input key class and set input value class, and you specify what is the class name and for your input key and for input value. That's very important because previous years, many of you follow this main driver, follow this main code, and just forget to mention the input key and input value data type, and that may cause some problems. So you need to remember that you need to think about if you need to configure the input key and input value class data types. And this is the file input format. This tells where to get the input file. So this is read from the arguments. And the first argument is the input folder, and the second argument is output folder. Both are in HDFS, or a local file system is also okay, just for testing. but normally it's in HDFS. So after we configure the input folder and output folder, next we can start the program. We can start the jobs. So wait for completion, and it will make the MapReduce job begin to run in your cluster, and wait until the job is finished. After the job is successfully finished, it will return true, and otherwise it will return false. So based on the true or false return value, you use system exit to tell your program whether the MapReduce job is successfully finished or there are some errors. So that's the main function. There are more configuration functions that could be used in this part, but now we just use these very basic configuration steps to configure the word count example. So in the lab, I hope that you could, so at least you could copy and paste the codes into an Eclipse project and then try to run the code to see if you can successfully compile the program and successfully run the program to generate the word count results by following the instructions provided in the lab. Okay, so here's some more explanations about the main function. This main function, this main class will start the MapReduce running, and the Hadoop system will pick up a bunch of values from the command lines on its own, and then the main function is the entry for the MapReduce program, and also get the parameters from the main function, such as input value, input folder and output folder to specify input-output paths. And also, if your program takes some parameters, you can also take from the from here, and then pass these parameters to your map jobs and to your reduce jobs. And the job is a primary interface for user to describe the MapReduce job to the Hadoop framework for execution. And okay, so here's the other parameters. In this example, we do not specify the number of reducers, right? So by default, there's only one reducer used in a MapReduce job. So if you want to use more than one reducer, you need to have a job.site number of reducers, for example, 2 or 3 or 4. So according to your configuration, the MapReduce will generate the corresponding number of reducers to do the reduce job. Okay. So that's all. That's about the main function explanation. So that's more details about the classes. So I think it's not very important at this stage. So for example, the job class, you just need to know that this is used to both the configuration and job objects are for you to use to configure your MapReduce job. And so later you'll see how you can configure. You can set the jar by class. So you need to provide the class location for your MapReduce job, and also provide the MapReduce class and set the output class, output key and value data type class, and input and output folder, and wait for the job to finish. Okay, so that's it. So as a whole, so normally, if there are very complicated problems, we need to have different classes for mapper, reducer, and the main or the driver class. But word count is a very easy problem. So you can see in this example, actually it integrates all the classes into a single file using static class. So this mapper is a static class, reducer is a static class, and word count, the main class, is used to wrap the two static classes. And the main function configures the word count problem. Okay, so that's what you need to program for this word count example. And that's about programming, about implementation. But next step is how to make it run in your computer. There are two ways. Well, using Eclipse is much more easier, but not that efficient because this is a IDE, okay? You can create a project and copy the code into a project, and then by using the Hadoop Eclipse plugins, so just run in just run this program by using the plugin, then you can see the results. And the file will also be generated on HDFS. But without using Eclipse, you can also use command lines. And it means that you first need to configure your environment variables. For example, the Java path and Hadoop class path, and then use some comment to compile your Java code to generate Java files. And this is about HDFS. Because we have learned HDFS, so you just need to know some HDFS command lines. This is very easy, very similar to what you do in your local system. For example, this is about HDFS to put your file into this input folder. So the input folder is in a directory in HDFS, not in your local system. And your file here is in your local system, file system. So you upload your local file to a directory in the HDFS folder. And then the Java code word count will read the input from this input folder and generate some results to the output folder, also in HDFS. You need to use the jar to run the application and then see the results. Okay, and finally, you can use some comment to check the results. It's not very interesting to introduce these steps because they are very practical. You need to do on your own. You need to practice. Okay, so I don't want to show too more details. Just remember that in the lab, try to compile the program in both ways, Eclipse and also in command line, because using Eclipse is for you to do the project, because it is more easier to debug, also to writing program, right? But for command lines, it's important for the marking, because we use the command line to run your program and to compare your output with our output for the correctness comparison. And that's it for this part. And this example for you to run in your lab. You can try to do this. You can create two files. One file contains this, and one file contains this sentence. For the two files, you just use HDFS command to upload the two files to the HDFS folder, input folder. And then you can run your program to see what will happen. So actually, the first map will emit these key value pairs, and the second map will emit these key value pairs. So the final output is like this. Values for the same key, for example, Hadoop will be combined to, and hello, two ones will be added together as two. You will see our output like this. So this can be used for you to test the correctness of your program. Okay. So that's about the practical part, how to write Java code in MapReduce. What I can do in class is only to do this boring introduction. The most important thing is that you practice on your own. Okay, you must be able to produce MapReduce projects, MapReduce job, MapReduce code, because that's very important for your first project. The first project is will be released next week, and you are going to write some code like this. Not very long piece of code, very long code, but you must be able to know how to write a program, how to debug your code, and how to check the errors, how to run your program, how to get the results, how to view the results, how to get the results from HDFS to your local file system. These things, these details, you can follow the lab instruction. Okay. For mappers and reducers, okay, so if you want to handle more data, much larger data set, and what you do is just add more mappers and reducers to deal with your data. And you do not need to handle multi-threaded code, because multi-thread computing is very, very complicated. I have tried some C++ multi-thread programming, and the experience is kind of a nightmare because too many details. I even cannot remember now. And now in MapReduce, so each mapper and each reducer job is actually only one thread, a single thread. So it's not like a multi-thread computing. And the mapper and reducers can run entirely independent for each other. They can run in parallel. But but things like, so the reducer must wait for the mapper. Okay, all the mappers finished, then the data will be shuffled and sorted, and then sent to the reducer for processing. And then the reducer can process these key value pairs in parallel. So there are two steps. So mappers finish, and then reducers begin. But for within the map step and within the reduce phase, so the mappers can run in parallel, and the reducer can run in parallel in separate JVMs. Okay. So before introducing the next concept, let's look at the word count example again to see if there's something where we can improve the program. Okay. So for example, using this example, hello world by world, and hello Hadoop, goodbye Hadoop. So for this sentence, we generate 4 key value pairs. And for this sentence, we also generate 4 key value pairs. And then we do aggregation for them, right? So it's okay to do this, but it means that if the documents is very, very large, and assume that this is documents of several hundred megabytes, and it means that for one term, we will have a lot of, for example, hello, we may have thousands of hello 1 key value pairs generated from one mapper output, right? So this is not very efficient. So a very simple way to improve is that you can group, do a locally group for these hello 1s to reduce the number of key value pairs generated from the mappers. Because so why we need to do this is so let's go back to the to this. Okay, this is a very simple example of how the data is transferred from the mapper to reducer. So we can see the results, intermediate results are generated from the mapper and stored in the mapper node. And then they must be copied to the reducer node. So if there are too many key value pairs, it means that the network cost and also I/O cost in this phase is very, very high. So we know, so that's why we try to reduce the cost, reduce the size of the intermediate results generated by the mapper. So if we can reduce the size of the intermediate results, so as a result, this phase can also have a lower cost. That's why in MapReduce, it introduces another concept called combiners. It will combine the intermediate results locally on one computer node to reduce the size of the intermediate results. This can help MapReduce to obtain better efficiency, to get better performance. So why we do this, the motivation has already been introduced. The reason is that a map task will reduce many pairs of the form, key, and value, right? So think about for the word count problem again. For one document, the term will appear many times. So as a result, we have many this term and 1 key value pairs for the same key, right? The popular words in the word count example just reviews this problem. So combiners is a general mechanism to reduce amount of intermediate data, thus saving the network time, because this intermediate data need to be copied from mapper node to reducer node. So by reducing the amount of the intermediate data, we reducing the network transfer time. This could be thought of as mini reducers because it's do a local aggregation, not like reducer do the global aggregation. So Well, the use of combiners must be thought carefully. And in Hadoop, it is optional. So the correctness of the algorithm cannot depend on the computation of the combiners. So it means that your program must guarantee that with or without combiner, your MapReduce program can always generate the correct output. So the combiner cannot affect the correctness of your program. Your program could not be affected by this combiner class. And a combiner operates on each map output key, so it must have the same output key value types as a mapper class. Okay, because like this sentence said, a combiner operates on each map output key. Okay, and a combiner can produce summary information from a large data set because it replaces original map output. So it's kind of local aggregation. So for the map output within one computation node, and we use combiner to locally combine the values for the same key. And this will help us to reduce the size of our intermediate results. And it works only if the reduce function is commutative and associative. So in general, reducer and combiner are not interchangeable. So you need to have a reducer and also have one combiner class. But sometimes you can use the reducer class also for the combiner class. For example, as in the word count, we can use the reducer as a combiner as well. Okay, so let's first look at the intuition. Look like from this example. The combiner combines the values of all keys of a single mapper node, a single machine, okay, a single mapper node, a single computation node. From this block, from this example, you can see we have two blocks. Okay, assume that this block is on one computer and this block is on another computer, and this is a mapper output. The mapper works on the record in this block and generates some results. For example, B1, C1, and these key value pairs. And this is in another computer. The mapper generates the output like this. Okay, without combiner, we just assume that the combiner is not here. Then shuffle and sort works directly on these key value pairs, these term and ones, right? We can see that many key value pairs need to be dealt with in this shuffle and sort phase. But what does combiner do? The combiner will do a local combination, a local aggregation. So here, this is the map output. The combiner will combine the values for the same key together. So as a result, after the combiner is applied in MapReduce, so the map output will be from this large amount to a much smaller size because the values for the same key is aggregated. And also on another computer, the same process is performed. And then shuffle and sort is performed on the smaller size intermediate results instead of the original intermediate results. So as a result, what we need to fetch from the mapper to the reducer is reduced significantly. We do not need to get so many key value pairs, but we only need to get a reduced size of key value pairs from mapper to reducer in this shuffle and sort phase. And then the reducer will do further aggregation. So the much less data needs to be copied and shuffled. So that's why combiners are very useful in MapReduce in many problems in order to get a better efficiency. And if combiners can take advantage of all opportunities for local aggregation, we have at most m times v intermediate key value pairs. So m is the number of mappers, and v is the number of unique terms in the collection. So on each mapper, we have at most v key value pairs. So in total, we have at most m times v intermediate key value pairs. But without combiner, it's much, much larger. It depends on the count of the terms. It's not just the size of the terms, the number of the terms. It is about the count, the frequency of the terms, which decides the size of the intermediate results. Okay. But in fact, not all mappers, not all computation nodes can see all the terms. It means that actually the size is much, much smaller than this worst case result. So by using the combiner, now we can obtain a much smaller intermediate key value pairs for later processing. And this reduces the network cost, also reduce I/O cost because the data are transformed from disk to disk. So by reducing the size of the intermediate results, we also save a lot of time on I/O cost and network cost. In word count, so what does the combiner do? It's just like the reducer. What the reducer do, the combiner will do the similar thing as a reducer. In word count, so you only need to add the following line to the main function. So you just need to use a reducer class as a combiner class. So set combiner class and use the same reducer class. So in MapReduce, it will also use the same reduce function for combining for the combiner. Okay, because in this example, the reducer and combiner they do the same thing, but please note that most cases this is not true. You need to write your own combiner for many problems, but in word count, you can use the same class for both reducer and combiners. What's the difference compared to the previous example? Remember that you have two sentences. Previously, the map output is 4 key value pairs, and both map functions has 4 key value pairs. But now after the combiner will combine the 4 key value pairs and generate 3 key value pairs as intermediate results. So now you can view that the map output is 3 key value pairs rather than 4 key value pairs, and this will be shuffled and sorted and then transferred to the reducers for processing. And you see now the size of the number of key value pairs is smaller, so we have better performance in MapReduce. So that's about combiner. Okay. So so far, I'm not sure if I'm too fast because during the past 1 hour, we have learned many new concepts. So I hope that you could be able to follow me on these concepts because these are very important for both your labs and your projects. In your first project, you need to implement a combiner for that problem. So you need to understand what does a combiner do, what is a combiner, what does a combiner do, and why a combiner can help your program to gain better performance. Okay. So far, is there any question? Okay. So now we need to move to next topic. It's called partitioner. This is about when you use more than one reducer. Okay, you need to use a partitioner. You need to define a partitioner. The reason is that, okay, so it still use word count as an example. And we have reducer, right? So if there's only one reducer, well, that's very easy. Now the output is just a sorted key value pairs, sorted term, according to their alphabetical order and their count, the frequency of each term. And then this will be generated as output of the single reducer, and the final output is just one file. But now if you are two reducers, okay, we have two reducers. The two reducers are used to process the different key and the list of values to deal with different terms. So now the question comes, how do I know this term and the list of values should be sent this reducer or sent to another reducer, right? So you need to make a decision for which reducer process which keys. And that's what a partitioner does. The partitioner controls the partitioning of the keys of the intermediate map outputs. Okay. The key is used to derive the partition, typically by a hash function. And the total number of partitions is the same as the number of reduced tasks or the reducers for this job. And this controls which of the unreduced tasks will process the intermediate key. For a given intermediate key, such as a term and a list of values. And first, we will use a hash function to compute a partition number for this key. Assume that this partition number is 2, and then if we have three reducers, so this will be sent to the second reducer for processing. So for each key value pairs, we will do such a hash function computation to decide which partition this key belongs to, and then we know that which reducer should be used to deal with this key value pair, deal with this intermediate key value pair. Why we need a partitioner? In MapReduce, it has a default partitioner, just a default hash function. So it means that without using defining a partitioner, you can also make your MapReduce program run without any problem. So for example, in word count, so you can use more than one reducer, it's okay. And you will see that your original one big word count result file is split into 2. So each is produced by one reducer. So some terms are within this file and some terms are within that file. It means that these terms are processed by this reducer and those terms are processed by that reducer. So that's it. Without defining a partitioner, so MapReduce will do this partition computation for you. Remember that you have a key, right? So they will have a default hash function to compute a partition for your key and then send to this key and list values to a certain reducer for processing. But in many applications, we need to define our own partitioner because we want to control the keys, which keys can be processed by which partitioners. Because we hope that some keys could be within one file for a later processing. So for example, assume that we have some websites, and each website is identified by its URL. So the URL is a unique identifier, is a key for these websites, right? So what we wish is that we wish that the URLs from a host end up in from the same host could be stored in the same file, could be processed by the same reducer. And how we can guarantee this? So without defining a partitioner, so the system by default will first get your URL of this web link, of this web page, and then use the URL to compute a hash value as a partition number. So it means that for the two URLs, for example, from USW, one faculties, one about us, or students, the hash function cannot guarantee that the two URLs will generate the same partition, okay? Because it's a hash function. How the hash is computed? It's a system default hash function. We do not know, and even you cannot design a hash function to guarantee that the two can be computed as a same partition number, right? So that's not possible. So what we can do this is we need to define our own partitioner. So in this partitioner, we first get the host name of this URL. So for this, we will get the host name as usw.edu.au, and for another one, they also have it also has the same host name. And then we use the host name to do the hash function, to compute the hash function, to compute the partition number. So for example, we first hash the host name of this URL, and mod RR is the number of partitions. So this can guarantee that the URLs from the same host will be processed by the same reducer. And as a result, they will be stored in the same file. But otherwise, if you do not first get the host name and then do this partitioner computation, they may send to different partitions. So they may spread across different nodes in your result. So that's what we do not expect. We expect that they can be in the same file. Okay.
These are the number of reducers?
Yeah, the R is the number of reducers and also the number of partitions. And you need to, after you define partitioner class, you need to set the partitioner class in the main function. Okay. The only thing is that I'm not sure if you understand this example. The example shows you the importance of partitioner. It can help us to control which keys are sent to which reducer. And as a result, they will be stored together for later processing. So any questions on this example? The reason is that if we compute the partition based on the original URL, it cannot guarantee that different URLs with the same host has the same partition number. But if we can first get the host name and then compute partition, it's guaranteed that they always have the same partition number because they have the same host name, right? Okay. Okay, so we have another rest break, and then we move to the next topic.
The URL, is that the key or the value of the
Key, you are the key, yeah. Value is a web key, web document.
So what if we have like unique keys? So how do we ensure that if we, because in here, like you say, if the key is 1, 2, 3, 4, 5, then how we can ensure that we partition into the same?
It depends on your problem. So for example, you have keys of integers, right, from 1 to 5.
Yeah.
And what you want to do is, for example, you want to make sure that from 1 to 2, you go to 1, from 3 to 5 to 2, right? So for the partitioner, you can design like this. You first get the key, and then use the key to compare with, not compare, use key to divide by the number of keys by 5. Right? So for if it is 2, and you divide 2 divided by 5 is 0.4, right? Then you use 0.4 to multiply by number of I didn't make it correct. Okay. Sorry. Okay. Let me think how to define a function for this. If you are only 2 reducers, okay, that's very easy. You just compare your key with number 2. So if your key is smaller than 2, so the partition is 1. If it's larger than 2, the partition is 2. So that's
just
all.
an if else statement, right?
Yes, but if there are more reducers, you need to do kind of a segmentation. So you need to compute this key is in which segment, and then this number of segment is a partition number for this key. So that's it.
Yeah. So, but it's possible to have.
Yes, possible.
With unique keys, we can still partition.
Can still be assigned to different partitions. You need to think about a way to do that.
Cool.
So if we hash on the same value, we're gonna have the same value again.
Sorry.
If we hash on the same key, then the hashed value is the same.
Yeah, it means that they have the same partition number. They will be sent to the same reducer.
They have the same partition number.
Yeah.
Okay, so what's the difference between hash on the URL and rather than on the key directly?
So in this example, if you do the hashing on original URL,
That means all of the key from this URL will be assigned to the same reducer. Is that right? If we have hash on the URL.
so if you hash it on URL, you also compute the partition. So that's fine, that's okay, it's not a problem.
I know.
So what I want to say is that if for this example, for the 2 URLs, you do the computation, the hash function of hash computation, they will have, they may have different partition numbers. So as a result, they are sent to different reducers. But what we wish is, what we expect that they are sent to the same reducer. We guarantee that they always be sent to the same reducer, always be stored in the same file. So that's what we want to do.
Yeah, that's what my question is.
Yeah,
So
yeah.
that means the key value pair from the same URL will be sent to the same reducer.
But the problem is that the URL is a key. It means that in your data set, there's no 2 records with the same URL.
Okay.
Because URL is the key. The key is always identify a record uniquely.
Okay.
Yeah.
Professor, why hash mod R? Why hash mod R?
Yeah, when we use mod, it's either 0 or 1, right?
Which one?
Mod.
Mod.
Why hash mod?
Oh, mod is just to compute. Mod is a math operator. To normally it's used in hash function. For example, it just computes the remainder of the first value divided by the second value.
Yeah, but why that?
Why that?
Why
Because
use mod? Because the result will be either 0 or 1.
no. We have we have R reducers.
Okay.
Yeah.
Right? We have a range from 0, 1, 2, 3, 4 until R. Yeah, we need the partition numbers are from 0 to R. From 0 to R minus 1. Yeah, we have R partition numbers from 0 to R minus 1. Yeah. So we use a mod R to guarantee that the partition number is within the range from 0 to R minus 1.
Still, it's like boxes. You are creating like each reducer is a box. When you calculate this number and do mod R, you get this guy, for example. This guy is going to go to the box number 1, which is the result of this one.
Yeah.
So other URL will have a different number. When you do mod R, if it is 2, we'll go to the box number 2.
Yeah.
The next one might be 2, but with different value also.
Yeah.
So it goes to the box number 2.
Yeah, that's true.
Okay.
So you know what does mod mean, right?
Yeah.
Okay.
Yeah. Can be
for
more
example-
than 0.
For example, 15 mod 7 is equal to 1. Right? So because
7 mod 4 is equals to 3. Right?
Then,
7 mod 4
yeah, it's
equals to 3.
Yeah.
Can be more. It's up to our mod. If it's 10, the mod can be 0 to 10. 0 to 9. Okay.
Yeah, there's one. Yeah.
Okay. Professor, last question. If I have 1,000 files, but I have only 10 computational nodes, how does this 1,000 files is going to be? Because I cannot launch 1,000 mappers because I don't have 1,000 nodes.
You can launch 1,000 mappers, but it means that one computer may run multiple mappers.
But it's going to be serial, right? One computation node, because I'm limited.
So you still remember one mapper corresponds to one thread. So it depends how many cores you have on.
No. Imagine that I have so many files that exceeds
But you need
from
to.
the amount of threads that
So
are.
it depends on the computing power of your cluster. Assume you have only 10 computers in your cluster, right? And maybe each computer has only 2 cores. And so at most you can have 20 mappers simultaneously running at the same time, right? So at the same time, there are only at most 20 mappers in your cluster. And then one mapper finished, so another task will be assigned to that.
Oh, it's like distributed system.
Yeah, it is a distributed system.
Yeah.
But it's going to be like serial 20 in 20. Not exactly, but it's going to be always at most 20. But it's going to be able, and Hadoop controls all of these.
Hadoop controls this. You don't need to care about how task is assigned to this idle thread, idle cores. Yeah.
So I can process 1 million files. It's only going to take longer.
It's just a matter of time.
Okay.
You just need to wait until it's finished.
Okay.
But there's no problem. Your class is able to deal with stuff like this.
Okay. All right.
Thank you. About the R, you said the R represent the number of
partitions.
and the reducer.
Yeah.
So why the petitioner and petitioner get the same amount?
Okay, it's because of the idea of partition. So partitioner is used to compute partition partition for this key. The partition means which reducer will process this key. Okay, so that's why the number of partitions and number of reducers is the same. So if they're not the same, you compute the partition number. For example, you have 3 reducers, but the partition number is 4. If you, for a key, you compute the partition number is 4, then you don't know that key is processed by which reducer, right? You have only 3 reducers. But now the partition number is 4. There's no 4th reducer for you to use.
Sorry, I don't get it. For example, the input of the partitioner, like six.
You have 6 partitioners.
Yes. No.
6 reducers.
I don't know how to describe it. For example, the input of the partitioner like is the 6 plus of the key
you mean the
value.
input?
Yeah, the input of the partitioner, and it divided. And then this misunderstanding of the function of the partitioner. You said
No,
it
it's not.
divided
It is divided. Divided
Yeah.
key space.
the key.
Yeah,
Yeah.
assume you have 6 keys.
Yeah,
Okay,
that's what I
fine.
mean.
Yeah.
And the partitioner will, and I have like 2 reducers,
2 reducers, yeah.
and the partitioner will divide the 6 into
2 groups.
2 groups.
Yeah, that's correct.
So why we need 2 partitioner? That's the question, because I think the partitioner is like a divider, divide the 6 keys into 2 groups.
That's true.
That is one partitioner do, right? Why 2 partitioners?
Not 2 partitioners. Yeah, that's only 1 partitioner, but that's 2 partitions.
Oh, you mean like
The
2
number of
nodes?
groups, yeah, number of groups, not the partitioners, not the number of partitioners, but the number of partitions. Yeah, only 1 partitioner is enough.
So in this case, I have 3 nodes.
Okay, so let's finish the last hour. Hopefully the partitioner concept is clear to you. So right now, we do not use partitioner in word count. So I guess that's why it is not very easy to understand. But in the next lecture, we will see more problems. And in those problems, we must have a partitioner to guarantee the correctness. Then you will see the usefulness of a partitioner, why we must use a partitioner. So this is just one simple example, but next week we will see more real and more practical problems. Okay, now let's recap the MapReduce. Let's review the MapReduce structure. So we already know MapReduce, that's what we have already be familiar with. But optionally, we also have combiner and partitioner. The combiner will combine the list of key and values from the same computer node, from the same node, to aggregate, to do a local aggregation for the node generated from the same computer to reduce the network cost, and then generate a list of qubit pairs. So you can see from the format, it is exactly the same format of the reducer. So it means that your data types of the combiner class must be exactly the same as the reducer class. It can be viewed as a mini reducer that runs in memory after the map phase. But remember, it's just an optimization. So you need to guarantee that with or without the combiner, your program is always correct, can always generate the correct output. A partitioner is used to compute a partition for a key. So it is given the key value pairs. So given the key space, the partitioner will partition the key space into several partitions, and each partition will be sent to one reducer for processing. Okay, so this is how partitioner does in a MapReduce. So often it is a simple hash of the keys to compute the partition for a key. It divides up the key space for parallel reduce operations. And so that's all what we need to define. We need to define MapReduce, the most important 2 functions. We need to tell MapReduce how to do the transformation in map, how to do the aggregation in reduce. And then optionally, we can also define combiner. So combiner is used to improve the performance, to gain better efficiency. Okay. For partitioner, it is used when we have more than one reducer. We have many reducers. And so since there are many reducers, we need to decide which keys should be processed by this reducer. and which keys should be processed by another reducer. So that's why partitioner is useful. And for all the other details, okay, Hadoop this framework will handle the system level details. Okay. So in MapReduce problem, the input data will always be split into fixed size pieces called input split. And Hadoop will create one map task for each input split. And the map task runs the user-defined map function for each record in the split. And so you can see that one map task for a split. But in one split, there are many records. So one record corresponds to one user-defined map function. Okay. Here you can see that one map task can invoke many times of map functions. Okay, so that's relationships between a map task and a map function. And one record is processed by one map function, and one split is dealt with by one map task. And the size of split depends on HDFS. Normally it's 64 megabytes or 128 megabytes. How to decide the size of splits is a very important problem in big data processing, because it could not be too large, and if it is too small, then you know there are too many splits. Then the overhead of managing the split will dominate the processing time, and it can also not be too large. If it's too large, then dealing with one split will be too complicated. And also, it's not easy to achieve load balancing, because some node will get many data records, but for the other node may get fewer records. So the load balancing is not very good. So how to balance this is a very important problem. And this 64 megabytes configuration follows Google's paper. So they have done some experiments to test what size should be suitable for most problems. And here is about some other optimization, locality optimization in MapReduce. Because it's difficult to move data to computation. So instead, in MapReduce, it moves computation to data. So where the data resides and where the map task is run. So it means that, for example, in this computer, okay, we have some data chunks, we have some input split, and then for this input split, a map task will be run on this computer, instead of moving the data from this computer to another one for processing. Okay, and also this is why the split size is same as the block size. And the map task will write their output to local disk. So this within the map node, the intermediate results are not written to HDFS. The intermediate results, such as in the word count, it's the term and a list of values, is output to the local disk. And then once the job is completed, well, the map output will be thrown away, will be removed from the local file system. And as a result, we do not store them in HDFS, because HDFS always replicates the data to guarantee the availability to deal with errors, failures. But for the intermediate results, it's not necessary to guarantee the availability, because they can only be used during the MapReduce job. After that, they are not useful. So that's why in MapReduce, it is only stored in a local file system, not in HDFS, which can guarantee the availability of the data. And as a result, if there are some failures, such as one node fails, some disk errors, and for the data on this node is lost, right? So Hadoop will rerun the map task on this node. Not on this node, rerun the task assigned to this node at another node to get the result. But the reduced tasks don't have the advantage of data locality, because the input of the reduced task is obtained from the map output instead of the original input data. So input to a single reduce task is normally the output because it's from all the mappers. So the output of reduce is stored in HDFS for reliability and also for chained MapReduce jobs. And the number of reduced tasks is not governed by the size of the input, but specified by the users, by us. We need to decide a good number of reducers for the reduced tasks. Okay. Here is some more details. I hope I can spend about 5 or 10 minutes to explain this step clear. This can help you to understand the MapReduce mechanism and also help you to understand MapReduce programming. This is internal mechanism of MapReduce. Previously, I didn't clearly explain the shuffle and sort phase, and now this figure can help you to understand how it is like. This figure is from the textbook, the Hadoop Definitive Guide. And also in that book, there are more explanations. So if you still could not be able to understand from this lecture, I hope that you could read the textbook to understand more details of the MapReduce mechanism. Okay. Okay, so let's begin to look at the figure and to understand the mechanism of MapReduce. So from the word count example, we can see how MapReduce is like. It gets some input, and input is split into some blocks. One block is called the input split. And each input split, like this, is processed by one map task. And within an input split, there are many records. Using word count as an example, so giving you a huge number of documents dataset, and each input split contains some documents. So say you have 10,000 documents, and then split into 10 input splits. So each input split may have, in average, have around 1,000 documents. Okay, so this 1,000 document will be processed by one map task. And then in one map task, each document will be processed by one map function. So there will be 1,000 map function calls within this map task. Okay, and each map function will process one document and then generate some intermediate result, some key value pairs, the terms, and count in in word count it is a value 1 in for this term. Okay, and these results will be buffered in memory. So now let's assume we use more than one. We use 3 reducers. We have 3 reducers in the reduce step. So now the problem is that for one key, which reducer is used to process this key, right? So that's where the partitioner is used. The partitioner will compute a partition for this key. So we can see that, assume this the map output of one map function, and the partitioner will compute a partition for a key, for a term. So for all the terms generated from this map function, and we have 3 partitions. So the keys are grouped into 3 sets. And the first group will be processed by the first reducer, and the second one will be processed by the second reducer. Okay, and from different map function output, so here we will do a merge on disk. So within this part, they are already sorted and partitioned, and this step is just a merge sort. So you can think about, we have a pointer pointing to each part. So there's pointer here, pointer here, pointer here. And so we move the 3 pointers simultaneously and then compare the data, the keys pointed by the 3 pointers, and compare the 3. And you select the smallest one and put it to here for each partition. So we use the first partition, for example. So we have 1 pointer here, 1 pointer here, 1 pointer here. We move them from the beginning to the end of this partition, and then select the smallest one and put it in here, put it here, and then select the next one, next smallest one pointed by the 3 pointers. So this is a merge sort. So after this merge step, so we can guarantee that within this partition, all the keys are sorted. And within this partition, all the keys are sorted. And here also for the third partition, all the keys are already sorted. These are the keys. So in the word count example, is the terms, together with list of values generated in this map task. And they are sorted according to the keys and stored, organized by the partitions computed for the keys. Okay, so we finish the mapper step. Now the map task finished like this. That's just for one mapper. And for the other input split, for the other documents chunk, we also do the same thing. So as a result, in each map task, we have a sorted, partitioned key value pair list. Okay, within each partition, they are already sorted, and then these keys are partitioned according to the partitioner you defined or system defined. So let's finish the map task. Now let's move to the reduce task. So remember that what does reduce task do? It receives a list of a key and a list of values for this key to do the aggregation, right? And now we have more than one reducer. We have 3 reducers. Now let's consider the first reducer. What we will do? The first reducer means that for the keys in the first partition from all the mappers will be sent to this reducer for processing, right? So as a result, this reducer will fetch the data from all the mappers. Because this is the first reducer, so only for the first mapper, it only gets the first partition, copied here, copied from this part to this part. And so in this example, also we have 4 mappers. So another chunk, another piece of data is copied from the first partition of the second mapper, and this is the first partition of the third mapper, and this is the first partition of the fourth mapper. They are fetched to the reduce node. Okay, and remember that for each partition, it's already sorted because it's already sorted within each map task. Sorted, 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 sorted. And what we want to do is we want to get a final sorted list of the key value pairs. So we do another merge sort. We merge the first partitions from all the mappers and obtain a final sorted key value pairs. And the reduce task will invoke a reduce function for each key received by this reducer, and then to generate output. So that's how the keys are processed from the mapper, the key value pairs are processed from the mapper to the reducer. Okay. Now data flow is like this. Input split is original data set. And then for each record in the input split, we have a map function to deal with it. And the map function will generate the intermediate results, key value pairs. And these key value pairs will be partitioned, computed according to the partitioner, and within each partition, it is sorted. And then for the output from different map functions, we need to merge them together as a long list. And again, the keys are grouped into different partitions to be processed by different reducers. And within each partition, it will be sorted. So that's our final output of the map task. Now next in the reduce task, so the first partition from different mappers will be processed by the first reducer. And the second partition of different map tasks will be processed by the second reducer. So as a result, take the first reduce task as an example. It will go to each mapper to fetch the first partition from them. And then, since all of them have already been sorted, and we just do a merge sort to get a final sorted key value pairs. And then the reduce task will invoke the reduce function to deal with them one by one according to the orders of the keys to generate the final output in this reduce task. Okay. So that's why we say that in MapReduce, we can only guarantee the order within the one reduce function, but we cannot guarantee that across different reducers, the keys are also ordered. So for example, we have 1, 2, 3, 4. We have 4 keys. So maybe 1 and 3 are sent to the first reducer for processing, but 2 and 4 may be sent to the second reducer for processing, right? So the result will be 1, 3, and 2, 4. So within each reducer, 1, 3, 2, 4, they are sorted, no problem. But across all the 2 reducers, 1, 3, 2, 4, it's not globally sorted. It's not a total order, right? So this is because of the mechanism of MapReduce. By just doing this, the total order cannot be guaranteed. Only partially order within the reduce function, within each reduce task, it can be guaranteed. So from here to here, is there any questions? So this is very important for you to understand the MapReduce task, how the MapReduce task is, how the data flow in MapReduce, how the data is transformed from the mapper and to the shuffle and the phase, sort phase, and how to transfer to the reduce function. And
could you give us some example about the merge parts?
Merge.
Yeah.
Okay.
Yes.
So all the merge, actually, they do the same thing. I'm not sure if you have learned merge sort. In the data structure and the algorithm course, you should know the merge sort, right? And it's similar to merge sort, but easier than merge sort. Because in merge sort, you merge 2 arrays together and to make it a sorted array. But it's not guaranteed that the 2 arrays are already sorted. So you still need to do some more tasks. But here, in this merge task, we can have, we already sorted the keys in each part, and then we just merge them together. And how to do the merge is like I said, we I think we use two arrays, maybe easier to explain. Okay, I can use now. I just use two arrays as an example. So we have 2 sorted arrays. Okay, one array, another array. They are all sorted. The task is to merge them as a single array, single sorted array. So that's what does a merge step do. Okay, so how we can do this? We maintain 2 pointers. One point to the first array, another point to the second array. Okay, so next is to put these keys or objects in the 2 arrays to the single array. Okay, now one pointer to here, one pointer to here. We compare to the 2 objects pointed by the 2 pointers. So which one is smaller? So if this one is smaller, now we copy this object to that array, and then we move this pointer to the next entry in this array. Now we get to move to a new object. Then we compare this one and this one. And then we again move the smaller one, copy the smaller one to that array. So we keep doing this. We keep moving the 2 pointers, and then we copy the smaller. We always copy the smaller object to that single array. So after the 2 pointers are moved to the tail of the 2 arrays, so we guarantee that that single array is also sorted. So that's the basic idea of the merge. So this guarantees that complexity is actually linear. So merge sort is all log n log n, right? That all n log n because of the original 2 arrays are not sorted. But now here, because we already do the sort, and so the merge step only causes linear complexity. You mean the record in the work example? The record is one document. the document ID is a key and the document itself is a value. So this key value pair is one record. It's called one record.
So one method can receive actually a couple, doesn't have to be one method can receive a couple files.
Yeah, so as a side, one map task can deal with multiple documents, multiple records. And one record is only processed by one map function. Yeah, that's it. Okay. So any more questions? Here's another figure, also try to explain the detailed MapReduce data flow. So actually, it explains the same thing from different input split. So in this example, we have 3 mappers and map tasks and 2 reduce tasks. So the data is split into 3 splits, and then each is processed by one map task. And one map task generates some output. Because there are 2 reducers, so each map task will generate the output partitioned into 2 groups. The first group will be processed by the first reducer, and the second group will be processed by the second reducer. Now, then the shuffle and sort phase, we need to fetch the data from the mapper to the reducer. So for the first reducer, we can see now the first partition from these mappers are copied to this reducer. And for the second reducer, the second partition are copied to this reducer. And then they merge the data as a single sorted list. And the reduce task will invoke reduce function to deal with them one by one according to the sorted order to then generate the final output. And so that's a higher level data flow in MapReduce. Okay.
Always one reducer is going to create one output file?
Sorry?
Always each reducer is going to create one output file?
Yeah, that's correct.
And why in some slides before there was only one output file?
If there's only one output file, just because we only use one reducer.
Okay.
If the number of output files depends on the number of reducers, so each reducer will generate one output file.
Can you go back 3 slides, please?
Which slides?
No, you're right.
Okay. You can try this in your lab. You can because the code provided in MapReduce use only one reducer, but we do not set the number of reducers, right? You can just add one line by doing job.set number of reducers 2. Then you will see in HDFS, you can see 2 output files. One start by part 0 and 0000, and then name with part 0001.
But the result on each output file is going to be sorted, right?
So within each input file, it is sorted.
But not amongst them. So one output file can start from A to R, and the second one B to Z.
It's possible. Or one input. Yeah, that's possible. Yeah.
Okay. No. Yeah, you're right.
But not A to R and B to
Yeah,
Z. That's not, because the key space is split into disjoint partitions. A to R and B to Z, they overlapped, you know. So one key can be only contained in one input file, output file.
Not because that files before is already sorted, right? So,
Okay, so now this is a more detailed view of MapReduce. So we have mapper and the map output, and then combiner will be applied to the map output on one computer node. Remember, it's on one computer node to combine the partially results and to reduce the size of the intermediate results. And next is the shuffle and sort. So the number that they will be computed at each key. We have to compute the partition for the key and then it will be sent to the corresponding reducer for processing. So that's it. From mapper, combiner, partitioner, shuffle and sort, and then reducer side. So this corresponds to this figure, and mapper and map output. Here we have a combiner, and then partitioner, and next we move to the reducer side. Okay, so now let's look at another example. It's also from the textbook, the Hadoop Definitive Guide. And this example shows a real problem, big data problem. It's also very simple, but you can see the power of MapReduce, how it can be used to solve some real-world problems efficiently. So this is a weather dataset from NCDC, National Climatic Data Center. It's a large volume of log data collected by weather sensors. So it's from the sensor, it's a sensor output. And the data format is like this. It's a line-oriented SQ2 format. And each record has many elements and focus on the temperature. We only focus on the temperature element. And now the query is that what is the highest recorded global temperature for each year in the dataset? So now look at the dataset. It's a dataset like this. Each line has a lot of information, but what we focus is we only focus on year, this part, and temperature, this part. This is the input format, input data, and output is the highest recorded global temperature for each year. So you see the output should be also at least a key value pairs. The key is a year, the value is the highest temperature, right? So that's what we want to do. And if without MapReduce, if you want to do this in Java or in some other kind of programming languages, or even by some scripts, it's a very easy task for small data set, right? You can just read the data one by one, and for each year, you only keep the current largest temperature, current highest temperature for this year. And when you read when you read the record, you just get the year and temperature, and compare this temperature with your current highest temperature, right? So if it is larger, then you replace the current one. If it is smaller, you discard the current one. And then after you scan data set, so the output is will be generated. The very easy task, right? The only problem is that how you can do this in big data set. For big data, very large scale data set. And here is an example for doing this using a command line with some Unix tools. So the author of this book, they did some experiments. They used awk for processing the line-oriented data. And for the whole data set, I remember it's about several hundred of gigabytes. Roughly of that size. And so after they complete and run for the century, just 100 years, it took 42 minutes on single EC2 high CPU extra large instance, which is provided by AWS. And 42 minutes for such a large data set. Now, the problem is that how we can improve this by using MapReduce, how we can parallelize this work. So to speed up the processing, okay, we need to run parts of the program in parallel, right? And what are the challenges? So we need to divide the work into even distribution to guarantee the load balance. So load balance normally is very important for distributed processing, because if the load is not balanced, then it means that some node get more data and some node gets fewer data. And as a result, the node which gets much more data dominates the whole processing time, and then distributed computing is not useful. So load balance is very important. But the problem is that the file size for different years varies, so it's not easy to guarantee load balance. And how to combine the results is also complicated, because get the result from the maximum temperature for each chunk. You can do that, but without the help of MapReduce, if you do the programming on your own, this is very complicated. And again, you are also still limited by the processing capacity of a single machine, because some data set grows beyond the capacity of a single machine. So although you try to distribute the data to different machines, but it is still possible that a single machine is not able to deal with the data assigned to it because of the limit of the computation power. And to use multiple machines, so you need to consider a variety of complex problems, so such as who runs the overall job and about reliability. But as we have learned before, so Hadoop has already hidden these details from us, right? So for these challenges, okay, it's not our problem. It's the Hadoop's task, Hadoop's duty to deal with challenges. So what we do, we focus on map and reduce. So now it's MapReduce problem design. And at least some of the questions you need to think about first before designing an algorithm for MapReduce for a problem. So you always need to think about these questions. So what are the map input key and value types? And next, okay, so let's think these questions about follow the data flow in MapReduce. Okay, first is about input of the mapper. And what is the input data type and what is the input value types? So next, after we fix data types, what does the mapper do for this job? So what kind of intermediate results should the mapper generate? And the next is about if we need a combiner to improve the efficiency. And if we want to use more than one reducer, and if so, if we need to define a partitioner to control the key assignment. And okay, now let's move to the reducer. What does the reducer do? And what should the aggregation be done in the reducer? And finally, what kind of the output key and value types should we use? So we need to think about these questions by following the data flow in MapReduce. Okay, and also we have more questions need to think about, so such as what are the file formats? And in word count, we use text formats, but actually in MapReduce, and also in many problems, the binary files are more commonly used instead of text files. So in this example, actually they used binary files rather than text files. And in MapReduce types, map receive key value pairs, generate list of key value pairs. For the reduce function, you must guarantee that the input of the reduce function is consistent with the output of the map function. Okay, so this must be guaranteed. Otherwise, you will receive some IO exceptions. And the combiner function is similar to the reducer. Okay. So it means that the data types of a combiner is exactly the same as a reducer. And the partitioner function takes input of key as an input and generate integer with a partition for this key as output. So that's different classes. And for this problem, you need to think about the question. You need to think about the question listed above. Okay, so now let's try to solve them one by one. And first, to identify input and output of the problem. So what is input and output? The input is, remember that it's a very large data set. Each record has a long line, right? So in this problem, you also do not use a key. So as a result, we can just use object as a key, just like in word count, because it's not useful. We are not using this key. And the value matters, so we need to think about what is a value like. So in the data set, we can see that, it is a string. Sorry, the file is still text file. So the value is a string. It means that we need to use text to wrap the record, to wrap the input value. And what is the output? So we the final output is the year and the temperature, maximum temperature, right? So the year could be either be integer or just a string, a 4-character string. And max temperature, in this example, is not float value, it's just integer. So we can use iterable to wrap the output value. Okay. So now, by analyzing the input and output, so we can decide the MapReduce data types by using text and int writable for these input and output data types. Okay. About writable wrappers, so I will skip this. We will try to go back to review this in the next lecture. Just list some wrapper classes for the Java primitive data types, for example, byte, short, int, float. And in your program, you need to think about which class you need to use to wrap your keys and values. So in this temperature example, we use text to wrap string, and we use int writable to wrap the highest temperature. Okay. Now it's about what does the mapper do. So we need to split this task into map task and reduce task, right? Now, okay, so the map task just need to extract the relevant information from the long record. And from the one line, actually, we just need to get the year and the corresponding temperature, right? And we also need to deal with some exceptions, such as bad records. We need to filter these bad records out. And that's it. Actually, we finished the map function. Because remember that in map function, it does a transformation. And in map function, what we do is to extract the information we want to use from the original record. So in this simple problem, that's already enough. We extract the year and the temperature from the original data set. That's it. Okay. And then the map input and output is just input is a data set, long text, and output is a year and the temperature in this record. Okay. That's it. That's about the mapper. And about combiner and partitioner. So if you use one reducer, then partitioner is not necessary. You only need to consider the partitioner when you use more than one reducer. If the combiner can help, so we will consider this problem later. Now we look at the reducer. What does the reducer do? By doing the transformation in mapper, so we can see that actually in reducer, it will receive a year and the list of temperatures for this year, right? So what does the reducer do? It's very obvious and also very straightforward. You just find the largest value from the list of temperatures, and this will be the final output for this year, right? You just scan all the values and then find the maximum one. The reducer just do a simple step to generate the final output. So as a whole, so for this problem, the MapReduce design is like this. So we get the year and temperature from the original data set, and then shuffle and sort. So the values for the same year will be grouped together. And this will be sent to the reducer for processing. So the reduce function reduce the list of values to the largest one. So we generate year and highest temperature. Okay, so that's it. It's a very easy task. The code can be seen like this, the source code, but I only emphasize the important part. So this in the mapper. So mapper extends the map class, and the most important line of the code is here. We get the year and the int writable for the temperature. Okay, and for the reducer, well, it's to do maximum value selection from the list of values, and that's it. We write the key and the maximum temperature out, and this is main function or the driver function, the driver class. So you can also find the code from this website. If you are interested, you can also download the code and run during the lab. Now, let's look at the combiner problem. here I set combiner class. So why we can use combiner to improve the efficiency? It's just because, okay, let's go back again. So let's look at what a mapper will output, right? So for a mapper, it will generate some a year and a temperature. And locally on one computer, it will generate a year and a list of values. Without the combiner, for each of the value, it has a corresponding key value pair. But with the combiner, so locally it will do a local aggregation. So it means that the temperature extracted from the data assigned to this computer, we only keep the largest one, and then the group shuffle and sort only work on the locally largest temperature. So in the shuffle and sort phase, the size of the intermediate results is reduced significantly, and as a result, the reduced phase is also much more efficient because the length of the list is much shorter comparing to without using the combiner. And in this example, we can use this reducer. Oh, sorry. We can use a reducer as a combiner. But